Hello and welcome back. In this video we'll start integration by parts, which is all about how to integrate something when the product rule comes up. So we're going to take the functions u and v, and I'm not sure really why they use u and v here instead of, say, other functions like f of x and g of x, but typically it's u and v. And we have seen the product rule, and we should be familiar with this. It says that if we take the derivative of two functions that are being multiplied together, what we do is we take one function times the derivative of the other, plus, and then we switch around, the second function times the derivative of the first. So, say another way to write this down would be u of x times v prime of x, say the derivative, plus v of x times u prime of x. So let's say that we want to come through and take an integral. So if I take the integral of the left-hand side, we've got the integral of the derivative of u of x times v of x. And when I take an integral of this right-hand side, when you take an integral of two things being added together, we can just take the integral of both of them individually. And technically I'm taking an antiderivative since there are no bounds, but in integrals may be a little bit easier to say than antiderivative. And what you'll notice is that on this side, if I'm taking the antiderivative of the derivative of something, well, antiderivatives and derivatives essentially can't cancel out. So the antiderivative and the derivative will cancel out. So I'll just be left with u times v on this side. Now, for the moment, I'm going to ignore constants because we know that when we integrate something, we'll just add a constant at the end. So for the moment, I'm just going to ignore all the constants that are popping out, and we'll take care of those at the end. And then I have the integral of ux times the derivative of v plus antiderivative of vx times the derivative of u. And what I'm going to do is I'm going to start replacing some things with differentials, because we know that if we have u of x and I want the differential of this guy, it's going to be ux dx. And if I have vx and I want to take its differential, I'll have v prime x dx. And this is where things get a little bit funky. Here, normally what we would do is we're going to write this slightly differently. So instead of writing u of x and having the of x there, we normally write just u. And then when we take the derivative, the differential of u is du. We treat this as if it's its own variable. And v, we write dv. I'm going to write this example a little bit. So let me rewrite this equation here. So u times v is just u times v. It's going to be equal to the integral of u dv plus the integral of v du. And if I solve for this integral here, the integral of u dv is going to be equal to u times v minus the integral of v du. This is the formula for integration by parts. So if we come up to a formula to some sort of integral that we're having trouble taking the integral of, taking the antiderivative of, one thing that we can do is we can try to use an integration by parts. What you'll notice is that we have a part that doesn't have the antiderivative in it, but we do switch it around, so we do have some integral with an antiderivative in it as well. But the hope is that we take a hard antiderivative and turn it into an easy one. So our goal when doing integration by parts is to take something that's hard that we can't really do by itself and turn it into an easier integral. So let's look at the integral that I had here, which was the antiderivative of x e to the x dx. So when we look at our formula, let me erase some of that and highlight it again. There are two things going on here. We have to identify what is u and what is dv. So here, when we look at this integral, the integral of, or the antiderivative of x e to the x is not something that I would know how to do just off the bat. I know how to integrate both of these parts. I know how to integrate x. I know how to integrate e to the x. E to the x is one of the nicest functions to integrate because it's just itself, e to the x. But together, when we multiply them, well, kind of looks like a product rule here. So we go, if there's a product rule involved, let's do integration by parts. So in here, we have to identify what is u and what is dv. So we need to identify u and v so that we can identify dv and du. And what I'm going to do is I'm going to show you what happens when we choose both things as u and dv. So we'll do this in two different ways, and I'll show you why one way works and why the other way doesn't. So for this first one, the trick here, and I'll just mention this trick first, is that u is going to be the one that turns into its derivative in the second integral. So for instance, x, if I had x as u, when I take the derivative of x, I just get 1. And this will turn into a 1. If I'm doing a differential, it'll just be 1 times dx. So if x here is u, that means that the rest of it is going to be dv. So this is going to be e to the x dx. So again, if this is my derivative, I have to undo the derivative to get back to v. So what function has a derivative equal to e to the x? It's just e to the x. So let's use our formula and do this first integration by parts. This is saying that the integral of x e to the x dx will be equal to, okay, so u times v minus the integral of v du. Well, e to the x times 1 is just e to the x, so why even bother writing a 1 there? And e to the x minus the antiderivative of e to the x. Well, the antiderivative of e to the x is just e to the x. And now that I have my final answer, I need to add plus c. That wasn't hard at all. Okay, and this was choosing x as u and choosing the rest of this as dv. What if we made a mistake and chose a different u and v? So let's say that maybe I go, oh, e to the x is easy to take the derivative of. So I'll make that u, so that when I find the second integral, when I try to find du, the derivative of e to the x is just e to the x. And that would mean that the rest of it, x dx, is going to be my dv. And when I integrate this to get back to v, the integral of x is just going to be x squared divided by 2. Again, we raise it to the 1 higher power and divide by that power. So now when I try to plug this into the formula, I'd say that the integral of x e to the x dx is going to be equal to u times v minus the integral of v du. But here, this also, we just made this integral even harder, right? Because our original integral is going to be x times e to the x dx. And now we've got an x squared times e to the x. This integral did not get simpler, which means that we probably didn't choose the right u and v. So this u and v don't work. This u and v will. Now, everything that I have written here is still correct. This integral is equal to this minus this. That is still absolutely true. It's just not helpful when we're trying to solve the question. Let's do another example. We have x plus 1 times the square root of x minus 1 dx. So right away, we notice, okay, we kind of have something that looks like a product rule here. This isn't very natural to take an integral of, so we want to use integration by parts. So we have to identify u and v so that we have du and dv. And what I'm going to do is right above this, I'm going to write down the actual formula. So the integral of u dv is u times v minus the integral of v du. So again, u is the thing that from our original integral to the second integral after the fact, we're going to end up taking the derivative. So we want something that we can take the derivative of that's going to be that's going to make our equation a lot simpler. So when we look at, okay, so essentially we've got two choices here. Which one of these do we want to be u? Well, if we chose the square root of x minus 1, we're going to have to take a derivative of that and then integrate something with that in it. Well, the derivative of the square root of x minus 1, that's going to be another square root of x minus 1, so it doesn't really get any simpler. So that's a bad choice. The choice that we want to make for u is x plus 1. Because what is the derivative of x plus 1 that's going to go into our second integral? The derivative of x is just 1. The derivative of 1 is just 0. And if I'm turning this into a differential, we have the dx at the end. But 1 plus 0 times dx, well, that's just dx. And that's a pretty simple thing to have in an integral. That means that whatever's left over has to be dv. And now I have to take this and find the original v. So let's integrate x minus 1 dx very, very quickly. Well, this is the same thing as x minus 1 to the 1/2 power. So we're going to raise it to the 3/2 power and divide by 3/2, which is the same thing as multiplying by 2 over 3. So v is going to be 2/3 x minus 1 to the 3/2. And now it's just sort of plug and chug, and we will watch as everything cleans up. So the integral of x plus 1, or I should say the antiderivative of x plus 1 times the square root of x minus 1 dx is going to be u times v minus the integral of v du, which is just dx.